Good morning again to everyone. This will be indeed the last lecture of my course, and we continue discussing statistics of eigenvectors of non-Hermitian random matrices. So in the first two lectures, we concentrated on the so-called diagonal Choker-Merich correlator, which is a characteristic of basically which describes statistics first, just the first moment, and then we discussed in our second lecture the whole distribution, which turned out to be heavy-tailed, of the diagonal entry of this matrix of overlaps, which we denoted as OKL. However, already in the first paper by Choker and Melich, they were able to evaluate, although not mathematically rigorously, but correctly, as later works by mathematicians showed, the object which is natural to call off-diagonal correlator, and which is just basically double sum involving these matrix elements of this overlap matrix between corresponding to eigenvalues zk and zl, different eigenvalues, weighted with the corresponding delta factor weights. So basically, we are this object characterizes these overlaps for eigenvalues located one around the point z in complex plane and another about around different point in the complex plane. And one is interested how this object behaves as a function of separation in the complex plane between z and z1 and z2, or z and z dash. Choker and Melich were able in their first paper to find the behavior of this correlator when, we remember that in our normalization, to stay within the bulk of so-called Genibert disk, we need to rescale z both coordinates with square root of n, and then in these new coordinates w, disk is already of order, of radius 1, and so in these coordinates they explicitly found the behavior for fixed w and w dash when n tends to infinity. Of course, when n tends to infinity, we have denser and denser eigenvalues in Genibert disk, and typical separation between nearest neighbors in complex plane is of order of in w coordinates of order of 1 over square root of n. Interesting question naturally arises whether one can also describe so-called microscopic behavior of this correlator at the distance of order 1 square root of n. In fact, this result for macroscopic, I believe, first was rigorously proved. I'm not sure in full generality, but at least important steps were done in paper by Walters and Starr, and then Bourgade and Dubac, they provided both macroscopic and microscopic values, for microscopic and for macroscopic separations. The goal of this last lecture will be to present explicit derivation of, in fact, I will concentrate on more difficult and in some sense more interesting object, which probably, or at least there is a hope to be universal, although it's not yet known. It's not, this object is only so far was computed even non-rigorously only for complex Genibert matrices. So we have only single example, but still, analytically. But numeric shows that microscopic behavior is universal. And interest to this object is added by growing interest to this off-diagonal correlators in theoretical physics literature. In the last 10 years, there was an essential interest in theoretical physics to study of non-Hermitian Hamiltonians, many-body Hamiltonians, describing so-called dissipative systems. For dissipative systems, necessarily these effective Hamiltonians, they become non-Hermitian and their eigenvalues scattered in the complex plane. And in particular, people were interested in characterizing in various regimes, which may involve, for example, so-called many-body localization. They checked numerically how this object behaves and found that in delocalized phase, as it's natural to expect, it's more or less numerically well described by behavior found for Genibor, but for localized phase and at transition, numerically, it demonstrates very different behavior. So there is essential interest in this object, and therefore it's useful to provide various ways of evaluating it. I will follow the same strategy to evaluate this object as I followed in the rest of these lectures. In fact, I did not find this way of derivation in the literature, so at least derivation is probably original, but the result, as I said, appeared in several papers, even at mathematical level of rigor. Okay, so we will use just this partial Schur decomposition as we already used for diagonal correlator successfully. But now we need, of course, to go one step further because we need to take into account overlaps of eigenvectors corresponding to two different eigenvalues. So let me remind you, this Schur decomposition is a representation, or if you like, coordinates on space of these Genibor matrices, which brings it to the form where we know that Z1 is eigenvalue of this matrix. Then one can bring it to the form that in the first column one has Z1 and then 0, and the rest is parameterized, I mean, in a natural way. And this transformation is performed by unitary Hermitian matrices P, which, I describe them in literature, they are known as householder reflection. And I put here a subindex Q showing that they are parameterized in terms of n-1 dimensional complex vector Q. I gave these formulas I think in the first lecture. Now we can naturally continue this procedure, just apply it again, the same transformation, but now to this block G1. And in this way, we bring it to similar form, just with G2 being n-2, size n-2 by n-2. Okay, and now the whole matrix is brought to such form with Z1 and then the first column with 0, and Z2, we have two entries which are non-zero. This entry, complex entry W, okay, I write it as W conjugated, and second eigenvalue Z2. And now these rotations are parameterized by by vectors Q1 and Q2. Okay. Now, again, one needs to recalculate Genibor measure, which is originally was given by exponential minus trace GG conjugate with respect to Lebesgue measure. We already did this calculation for first step, and of course, it's just straightforward to continue it to the second step. So I give here the result of this. So one will get some factor, which I do not specify, which depends on these vectors Q parameterizing Householder transformation. We won't need them for our calculation because basically the objects we're interested in, they are not dependent on this. We will have purely Gaussian standard variables here, I mean, in this entry W, and for both vectors W1 and W2, and they are uncorrelated and standard Gaussian variables. And we now have, not surprisingly, two modulus square of characteristic polynomials for this block of size n-2. And we have, and this block is itself Genebra-like distributed. And there is some restriction on integration with respect to vectors Q, but as I said, for us, it's of secondary importance. But one can formulate questions where this will be important, but it's not what we are going to discuss today. Okay. Now, as before, in this form, it's easy to write left and right eigenvectors of the whole matrix. I remind you that since rotation is unitary and Hermitian, we just have that corresponding rotation matrix when squared is equal to identity, and therefore just it's enough just to consider left and right eigenvectors of this central part are matrix of overlaps remains invariant with respect to this transformation. Now, again, we've already seen that right eigenvalues are very simple. So the first one is just, again, 1 and then 0, the most simple it can be. R2 is easy to find. It's just of this form. It has two non-zero components. First one is given by ratio of this variable W divided by difference between eigenvalues. And now substituting this type of the matrix into by orthonormality condition, we remember that, for example, L1 will be is orthogonal to R1 and not even orthogonal, but orthonormal. So it should be the scalar product should be 1, but it's orthogonal to also to R2. Sorry, and this dictates such a form for L1 first left eigenvector, and then substituting it to left eigenequation, one in the same way as we did in the first lecture. One just solves it immediately for this remaining and most important part, B1, and one finds, not surprisingly, that it's just basically given by action of combination of vectors W1 and W2 to the resolvent of this block G2. But we're interested in the resolvent at spectral value corresponding to the first eigenvalue. Finally, one finds also by heteronormality L2 should be in the form 0, 1, and then some vector, and this vector is easy to find again substituting by equation. Now we remember that important role was played by in our previous computation of diagonal correlator and also for the distribution of diagonal entries of matrix O. It was played by Hermitian matrix B, which was just basically squared characteristic matrix of the corresponding block G. Here, similar matrix appears, but it's slightly more involved. It's not Hermitian any longer because these two factors contain two different spectral parameters. So if Z1 and Z2 are the same, it would be our previous matrix B with which we worked successfully. Here I just call it B tilde just to show that it's slightly different. But it's not Hermitian because of Z1 and Z2 being different. Now, so one should be careful with this a little bit. In terms of this matrix, we just explicitly write overlap. I mean, the off-diagonal element of this matrix, which we're interested in, between left and right eigenvectors of corresponding to eigenvalues 1 and 2, Z1 and Z2. So this is the object. It's a little bit more complicated than for diagonal case. It's expected. It has also these denominators. I forgot. Maybe I should go back to this measure and just draw attention to a new factor. When one does this further, this decomposition and recalculates measure, naturally the factor appears, which we expect it to appear. It's element or building element, or eventually when one will do these steps to the end, just if we complete short decomposition, we know that important object, probably the most important object, will be squared modulus of van der Monde determinant. So it's natural that when we have two eigenvalues, this difference of moduli squared appears. This is element of this product. So it will be product of over all pairs Zi minus Zj modulus squared. Here it just appears first. So when we see objects appearing here in denominator, we should not be worried because basically when we integrate with respect to the measure, this singularly looking terms will be benign. Okay, but so what we need to do, we need to take this and average over that probability measure that we just derived. The first step is simple. We remember the W's, vectors W's, they are just independent Gaussian distributed normal standard variables. Also W, this scalar W is the Gaussian. So we can easily perform this averaging over these random variables. And the result will be that just when we perform averaging over all W's, this is the result for common result. So it's very similar to what we've seen before, but instead of B, matrix B, we have trace of this tilde B, inverse tilde B. We also have this factor here. And of course, now it should we should multiply this with two delta function factors fixing position of our eigenvalues in the complex plane, and then we need to average the result over distributions of G2. And remembering that in Genebra measure comes factor which cancels this 1 over Z1 minus Z2 squared. Okay, so doing this, we arrive to the problem of evaluating expectation over n-2 by n-2 Genebra matrices of this object and multiply it with product of two modulus squared of characteristic polynomials, each centered at position at one point and at the other point. Now it's recalling definition of the matrix B tilde. We see that in fact modulus of its determinant square is exactly this factor. So one can again write everything only in terms of this matrix B, and this is helpful because we just follow the same basically the same trick that we applied already when calculating expectation of diagonal entries. One can introduce a matrix which is made of blocks of size, so matrix of size 2n by 2n, made of these blocks of size n by n. On diagonal, we have again this auxiliary variable over which we should differentiate to produce such a combination. And off diagonal, we have characteristic matrices at two different values of parameter z. This is the difference. So now this matrix depends on three parameters, on auxiliary parameter mu, over which we differentiate, and over two positions in the complex plane. And we need to evaluate, for brevity, I will call this Tn minus 2, is just this average of this product over Genibor matrices, and then differentiate and set parameter mu to 0. Exactly the same construction. So up to this point, and even maybe a few steps further, or few slides further, procedure follows exactly the same steps as for diagonal correlators. But let me just remind you, I think it's useful to remind again this procedure. So we use Grassmann vectors to represent each of these determinants in a standard way. So one Gaussian, one Gaussian variable set of Gaussian integral to represent one determinant, and then to represent second determinant. And we now already remember how we perform averaging of Genibor matrices. It's done by using this nice identity, but now matrices A will be made of some combination of this B. So it's in fact goes again parallel. It goes in some sense very close to part of our supersymmetry calculation yesterday in second lecture, because there we dealt with squared determinant. Square determinant is also determinant times determinant. So structure is very similar to what we've seen, but there is some subtlety in different spectral parameters, but technically it's not very essential here. Again, we need to introduce, first steps here, it's even simpler because we do not have extra commuting integral which represented denominator. Yesterday in supersymmetric calculation, we had also one determinant in the denominator, and it eventually, after averaging, was mixed with Grassmann variables. Here it's slightly simpler even, because we deal only with Grassmann integrals, but we remember that even for this part, we need to introduce 2 by 2 matrices made of bilinear combinations of Grassmann vectors. And after straightforward manipulations, we just notice that this object, exponential minus trace AB, is nothing else as exponential minus trace of this product of these two matrices. Now it's already clear what we should do. We should use a matrix version of Hubbard-Stratonich transformation to decouple these two matrices and perform back rising Gaussian integral over Grassmann vectors. So we do this exactly. So in order to decouple, we introduce general complex 2 by 2 matrix Q, and then use this identity that we discussed yesterday. And then basically in integration, if we introduce this notation for long Grassmann vectors containing 4n components, for phi it's this, for psi it's that, then one just noticed that after this Hubbard-Stratonich decoupling, we just express everything as bilinear form in phi and psi, and therefore corresponding integrals will be, as I mentioned, just Gaussian, and we get relatively simple, or at least simply looking, but we will see that in fact it has a lot of subtleties in it, expression for the object of interest. Again, I here performed for simplicity average over Genibor matrices of size n by n. In the end, we need to replace n with n minus 2, but this is simple, of course. Okay, so here a few new notations appeared, which was not used before. We need matrices, such matrices, which you call capital sigma here, which just 2 by 2 matrices with matrix with only one non-vanishing entry in top left corner. They rise, basically they take care of this auxiliary matrices, auxiliary variable mu is multiplied with this sigma, and it will play some essential role later on. Now in this form, so the goal is eventually to evaluate asymptotic. Of course, one can be interested also in studying for finite n the behavior of diagonal correlator. In principle, it's possible, but in practice, we are interested always in random matrix theory, with very few exceptions, in asymptotic behavior when n tends to infinity. In order to facilitate dealing with this integral, I find it expedient just to make a trivial shift, just replace Q plus this matrix with just Q. By this change, we just move dependence of mu to the exponent, which is more convenient for further evaluation. Now we, as I mentioned, we're interested in a asymptotic regime. There we need to rescale our z and our position in the complex plane with square root of n in order to stay in the bulk. It's so-called this random matrix jargon. The bulk is within support of the limiting measure so within the Genibor disk. In principle, the same construction can be used, but it will be somewhat more involved. In fact, I don't know if it's done. I don't think it's done. Maybe I should do it after this lecture. One can be interested in analyzing behavior of the same object at the edge of Genibor. I did not mention this, but probably you already heard in other lectures that the behavior of various interesting quantities in random matrix theory is usually has two types of universalities. For one of them, one takes observation points or two observation points, like in our case, both in the support of the limiting measure. This is called bulk behavior. But one can also basically tune our parameters in such a way that in the limit n to infinity, we are in some meaningful vicinity of the edge of the support. And then usually limiting behavior is different. I won't analyze it there in neither of these quantities. For diagonal correlators, it can be found in the literature. It was analyzed. I should check whether it was analyzed also for off-diagonal. But it can be done. But we are just again coming back to the main topic. We are interested in keeping both parameters W and W dash fixed and maybe not fixed. We will discuss later on in which sense they are fixed, but at least modulus of them smaller than 1 to keep observation points inside the bulk. So we have then our main object of interest as integral, which I write in such form, in suggestive form, and this exponential, which in physicist jargon will be called action, but it's just exponential, which contains a big factor in front, which is suggestive of applying Laplace or saddle point method for extracting the asymptotics. So this exponential has the following form. The first term is just trace of Q times its conjugate. Second term is proportional to this parameter square root of mu. So we should remember that eventually we need to differentiate over mu and set mu to 0. So this term should not be taken into account or should be taken into account appropriately when performing this expected saddle point evaluation. And then we have a logarithm.
I have a question about this term, square root of mu, trace sigma. Yeah. So why do we have a factor n in front of it, not square root of n?
Good question. I'm not sure how it's. Okay, I need to check. Maybe it was a misprint. Maybe I think it should be square root of n. Yes, indeed. And okay, let me just. We will see in the next slide. Maybe I corrected it. I think it should be square root of n. It's just a misprint. So, but anyway, my message was that basically it's not a part of saddle point game anyway, because or at least a special part, because this mu eventually set to 0, so one should be careful in taking it into account. Now, and there is also this term which is basically exponentiation. It was determinant to power n, so it's log that. Now, we will concentrate in the rest of this lecture on microscopic scaling regime, where separation between these scale positions, W's, inside Gini-Hilbert disk of order of typical separation between eigenvalues in the bulk. So in order to take this into account, it's natural just to scale. So the difference between these two variables, W, W dash, is of order 1 or square root of n. So corresponding coefficient in front I will call capital omega. So capital omega is the difference measured in the units of square root of n. And common position inside this disk I will call small case omega. So small case omega will be for fixing observation point, and capital omega is just separation between observation points. Also, when we substitute it back, we see then that basically this matrix inside determinant can be represented as sum of two terms, one is principal term, and there is subleading term of order 1 square root of n. And in order to write it briefly, one needs to introduce this important matrix lambda, which is 1 in a diagonal matrix 1 minus 1. Okay, so no, I still do not quite remember. No, it's still not. Okay, I need to check whether it's n or square root of n here. It appears like n, but I'm not sure. We will see. Anyway, so now I write really this integrand in product of three different terms. Why one term is just involving these mu's over which we eventually differentiate. It should not mix up in our saddle point evaluation. Now we see that I just included part of the determinant which is leading naturally, which has this factor n into this part which I called L naught, which really controls the saddle point in our in the limit n to infinity. And there is this second part, subleading part in the determinant, which I separated here, and matrix D is okay. How one gets it? So one has determinant of this sum. So I just take this as a factor, and then I will have 1 plus inverse of this matrix times this object. And this is exactly what is written here. Inverse of this matrix times this object. This is unpleasantly looking combinations, but we will see they are not that bad after all. So how to analyze this integral? Still, we should separate degrees of freedom which are clearly controlled by saddle points and some other remaining degrees of freedom. And this is most naturally can be done by, I mean, there are several ways of doing this, but I will do it by employing, again, already familiar to us, singular value decomposition of matrices Q. So this is, again, representation of integration variables in terms of diagonal matrix of positive numbers R1 and R2, and two rotation matrices, which are unitary. And this transformation from general complex matrices to these coordinates incurs this Jacobian that I already mentioned, I think, in one of previous lectures. It's 2 by 2. Oops. And it has this characteristic factor, one again squared van der Monde determinant of this R1 and R2. This is standard. Now, this d mu u, d mu HV is just Haar measure on group of unitary 2 by 2 matrices. And in this way, we see that this in these coordinates, we see that we get really the part of this exponent which is controlled by, which should be treated by and can be treated by saddle point method. So it consists of, basically it's decouples in variables R1 and R2. So one can do this separately in R1 and R2. And exponential in each of these variables is just very simple. It's R minus log of R plus modulus of squared modulus of observation position. So we are looking for stationary points just of this expression, or in fact, we are looking for minima in order to apply saddle point method in Laplace version. Basically, we immediately see that indeed corresponding integrals will be dominated by points of minimum at R1 equal R2 equal 1 minus modulus of omega squared, as long as we are inside the Genibor disk. These values are positive, and this compatible with integration domain being from 0 to infinity. If omega goes beyond 1, then of course saddle point method should be modified because we come to boundary of the integration domain. But we are always considering this as positive quantity, so it's relatively simple. But we see that only part of these variables are controlled by, I mean, namely, these radial variables R1 and R2 are fully controlled by saddle point evaluation, but these matrices U and V, they freely rotate. And this is a situation when we have some saddle point which is rotated. This usually gives rise to so-called nonlinear sigma model, and we will see that we indeed get to integrals of that form. When we come to it, I will show it. But okay, so what should be done now technically? We have these saddle points, but we need also to evaluate fluctuations around saddle points. So we should expand around saddle points and perform corresponding integrals. Recall the presence of the factor R1 minus R2 squared, and at the saddle point, R1 and R2 are equal. So in the leading order they vanish, and but this part is controlled by deviation from the saddle point. All this should be very accurately taken into account. So we just expand. We expand around these values and just consider for large n, introduce these deviations which we expect to be of order 1 or square root of n. and we introduce the matrix of these deviations from the saddle point. Correspondingly, this Vandermonde factor is just difference between these variables zeta1 and zeta2 squared. And then we should very accurately expand everywhere in other terms, keeping leading, and we will see that we in fact leading terms will vanish. I mean, naively. So what to do naively? We should do the following. We should take this term and again exponentiate and expand using small parameters. But we will see that first term of expansion vanish, and we need to expand to the next term, which will be of order 1 over n. Multiplying with n, it will give us something of order 1 in exponential. So this is how it all done. We should accurately take these objects which enter this matrix D. We see we have these denominators and also numerators Q. We should substitute parameterization here and accurately expand, keeping leading and subleading terms. In fact, it's always, I mean, just practical advice, it's useful to expand to next, not only to leading terms, but to subleading terms, and just to control, to see how they compare, because what looks like leading may vanish. Here I just show this expansion, which one obtains after substituting and doing accurate expansion around, around the saddle point. So we see this is seemingly leading part, and this is next term. But when we, as I mentioned again, when we evaluate this in the limit of large n, we basically have in exponential, we have trace of log of 1 plus something. So we expand it in Taylor series, and this is the leading term, but trace will vanish because of the fact that lambda matrix is 1 minus 1, and its trace vanishes. So this term vanishes. So the term which is actually leading is 1 over of order 1 over n, and therefore when exponentiated, it gives us something of order of unity. Okay, and this taking this into account, we get the leading order behavior when for large n of this form. It's what we have, what we should substitute back to our integrand, and we substituted back to the integral, collect all terms, and then we see that basically the manifold over which we integrate these fluctuations, which we'd like to compute, Gaussian fluctuations, they're basically not only Gaussian fluctuations which we do, which are accumulated in this side, but also we have these rotations which should be taken into account. And in this way, we just see that we have, in fact, Gaussian integrations of matrices Z. So this is the structure to which we arrive. Okay, some factors which are accumulated outside the integral. Then integral which goes over matrices U naught. I think I forgot to introduce this U naught is basically a product of two unitary matrices. When doing this singular value decomposition, we had matrix U, which is unitary 2 by 2, and matrix V, which is.
I saw you not in the previous slide.
I gave it, right? Yes. I just forgot to mention it explicitly. So indeed, the product of these two matrices, left and right unitary 2 by 2 matrices used in singular value decomposition, enters resulting expression only in the product. So therefore, it's natural to this unitary matrix and it's natural to use notation for it, since only this combination happens. Then basically we have therefore three integrals. Two integrals. We have extra factors which are not integrated. Now, non-trivial integral over unitary matrices, 2 by 2 matrices U naught, and Gaussian integral over these matrices 2 by 2 Hermitian matrices. Basically, this is a parameterization of Gaussian fluctuation, relevant Gaussian fluctuations around the saddle point. And we here, we introduced here this matrix T, again made of, it depends on these unitary matrices. So basically, this is a Gaussian integral. That's important. Gaussian integral gives us a trace of this matrix T squared. And therefore, it gives new terms depending on U naught, which are of the same order and should be combined with all terms that we have. And we are practically done. We arrive after all these manipulations to integral which physicists called a nonlinear sigma model. Basically, if you don't like this terminology, it's fine. It's integral over unitary group, but its origin is in degeneracy of the saddle point. So only part of variables are controlled by saddle point, but it can be rotated by some combinations of unitary matrices. And in such a situation, non-trivial integrals are given by group integrals, not just by saddle point, but by need to evaluate some group integral. This situation is standard in random matrix theory when one calculates some correlation functions, for example, of eigenvalues or of characteristic polynomials. Maybe you were already given some discussion of this in context of Hermitian matrices. Here is non-Hermitian analog of this. Now, remaining job is to evaluate this integral, and this can be done most expediently if one uses just explicit parameterization for 2 by 2 unitary matrices, which for your benefit I represent here explicitly. So we have here parameters theta, going between 0 and 2 pi, and also these angles of alpha 1, alpha 2, and phi. Corresponding Haar measure is easy to write in these coordinates. And recalling definitions of these two matrices, lambda and sigma, we evaluate all terms which we need for our computation. Basically, we can first to perform integral over this alpha. We see that one can perform integrals over alphas. I think it should be alpha 1 here probably. Alpha 1 in exponent. These are integrals which give standard table integrals giving so-called modified Bessel function or Bessel function of imaginary argument. As a result, we obtain this object, our main object of interest, as basically one integral remains here. For finite mu, one integral remains. But we remember that in the end, we need to differentiate over mu and set mu to 0. Then when we set mu to 0, argument of Bessel function after differentiation will be 0. So for I0, it will just be, some constant. For I1, it will combine with something else and either vanish or give some finite contribution, and the result will be easy to integrate, will be just a simple integral. So all in all, substituting this expression to differentiating this over mu, substituting to expression that we derived in the beginning, one gets the limit after a few lines of calculation, and this is explicit result for off-diagonal correlator. It's exactly the same as found by Bourgaert and Dubas without resort to this Grassmann integration and arising nonlinear sigma model. This is alternative derivation, and basically, I think, apart from the fact that I think it's interesting by itself, this derivation, which shows power of this method, it also may have utility beyond the method of Bourgaert and Dubas, namely in beautiful recent papers by Mohammed Osman. Basically, it was shown how to prove universality for general classes of matrices of non-Hermitian matrices with independent, identically distributed entries, so-called Wigner matrices, with finite moment, with finite second moment at least. Although it's not yet done, but the best way to address this problem, as Osman showed, is to use this partial Schur decomposition. Since universality for this object, for off-diagonal correlator, was never considered, I believe that this method can be used to prove universality following, but it requires certain generalization of Osman's work, but I believe it's doable. And with this, I finish this last lecture. Thank you for your attention.